Here's a differentiation question from C1. Right, a few things I might mention here. One, this here, we see a lot more of this type of thing in C3. It means the domain of the function. We really don't need to worry about it here because it just wants dy by dx. And we can almost, the comma, any time you see a function written with a comma and nothing after it, that's actually what's called is the domain, or the actual values for which a function is valid. We don't really need to worry about it in C1 and C2. It's just a kind of pure mathematical definition of the function. So in order to differentiate, we really need to get into before we differentiate, into AP to the AX to the P plus BX to the Q plus CX to the R, running out of letters now, but you get the picture. We need to get it into individual powers of X. We've got an issue here, an easy one to resolve on top. Obviously we multiply out, but then we need to use indices because of or some other form of algebra or whatever to deal with the X on the bottom. Okay, right, now, sorry about them moving around to the screen there. Okay, now, so let's go back. Right, let's do it. Right, now, let's multiply at the top. We've already got it written above, so we might as well just multiply x squared. Then we get 8x plus 3x, so that's minus 8x plus 3x, so that's minus 5x. And then we get minus 24 all over x. Now probably we can deal with this in a number of ways, but I like to just split it because it's easier to see then. We clearly know that because it's got a common denominator of x, so we can split the kind of fraction up in that way. And that gives us x minus 5 minus 24 x to the minus 1. All we've done, as I said now, is written it in the form where we can differentiate and use our rule for differentiation, which is nx to the n minus 1 dy by dx. We can use that. Okay, so dy by dx, the first one is 1. The 5 just disappears because it's a constant, so that goes. And here we've got minus 24 times minus 1 x to the minus 2. So that's simplifying it down. 1 plus 24 x to the minus 2. So that's 1 plus 24 over x squared. Okay, so that's part A done. Now for part B, it says find the equation of the tangent, not the normal, the tangent, when x equals 2. Well, we need to find a y coordinate when x equals 2, because we need a coordinate and we need a gradient, and we need to put the 2 into the formula for dy by dx. So let's work out the y coordinate first. So when x equals 2, y equals to, I can just use the top bit there, 5 for that bit, and for this bit 2 minus 8 is minus 6 divided by 2, so that's minus 30 over 2, so that's minus 15, and dy by dx equals 1 plus 24 over 2 squared. So that equals to, that's 24 divided by 4, which is equal to 24 divided by 4 is 6, but plus the 1, which is 7. So divided by the x is 7. So now we've got a coordinate, 2 minus 15, and we've got a gradient of 7. So that's all we need to use y minus y1 equals mx minus x1. So y plus 15 is equal to 7 x minus 2. And when we multiply that out, we get y plus 15 is equal to 7x minus 14. So y is equal to 7x minus 29. Okay, we've done the question, and the graph sketching for this is way beyond what you'd be expected in C1. For those of you who are look in A2 level, or certainly further or certain levels, it is the kind of thing we would expect you to be able to sketch, certainly at a certain level, but certainly way beyond what would be expected at C1. So we didn't really need to graph it to actually be able to answer the question, but we can see, here we go, the answer confirmed by GeoGebra there. If you look on the left hand of the screen, if I try and I've just managed to lock it into the correct answer there. There we go, minus 15. Okay, that's the actual, the gradient changes. Okay, and we get it over, we get the answer as we did. Let's get back to it. Minus 2, trying to get the A coordinate locked into, there we go, again, finally, want to finish off on that. Yay, there we go, locked onto the actual coordinate, which gives us a tangent of 7x minus 29. And that's it, folks.